Hello. I've said a lot about dark energy model, but not everything. So here we are, at this point, a computer model for the entire galaxy.
Będzie to model ciemnej energii dla całej galaktyki.
A galactic model of dark energy for all types of stars in the galaxy. There are different types of stars in the galaxy: smaller, medium, larger, and very large. The presented model applies to all types of stars. Small astronomical objects are not included: planets, moons, asteroids, planetoids, cosmic dust, gas clouds. I also ignore black holes. I have already shown calculations for the black holes. The results of calculations for the black hole can be added to the galactic model. Most of the masses of galaxy is the mass of its stars. The calculations are possible. This model is probably not perfect or very precise. It's radar and estimate. I invite you to watch. A dark energy model for the galaxy. I will use program Mathcad 15. You can choose one of the other programs. You can choose your preferred version. Here are the online links to the files for all model versions. One link is enough to download the file, zip archive. It must be unpacked on your computer's hard drive. After unpacking the file, the program directories will be available. The appropriate models are contained in the folders. One link is enough. I prepared several copies. If one service stops working, you should choose another one. There are stars of different sizes in a galaxy. This phenomenon has its own astronomical name, spectral types of stars. This version of dark energy model takes into account all spectral types of stars. Only stars, as I said. Table copied from the internet. Data comes from Wikipedia. The table lists the spectral types of stars. Here, the spectral types of stars. The most important data is the column with the value of the star's mass and the column with the value of the star's radius. The percentage distribution of stars in the galaxy is also very important. Notice here the mass column. The mass of the star is written as relative mass. The mass of the star relative to the mass of the Sun. Example 1. The mass of the star is 16 solar masses. Example 2. The mass of the star is given in the range from 2.1 to 16 solar masses. This range of mass is characteristic for this type of star. Similarly, for the star radius, the radius is relative. The radius range for the selected star type is given. As before, we need to divide the object into layers. A thousand layers, a million layers, as many layers as we want. In this case, it's a star. I choose a linear density distribution. It's possible that the density distribution inside the star is not linear. The star is probably denser in the center. If we know the density distribution, we can use it. This allows to improve the calculation results. I do not have such a dataset. I assumed a linear density distribution for the object. If there is divergence, it shouldn't be large. It should be noted that this is only an estimate. The calculations are not super precise. There are many different types of stars in a galaxy. Stars of different sizes shown in cross-section. Stars in the galaxy. The galaxy contains an infinite number of stars. No, the galaxy contains a very large number of stars of different sizes. Billions of stars. The Milky Way contains about 400 billion stars. We select the appropriate folder. We run the file with the model. Dark energy model for the galaxy. The program has already run. We start by declaring the base variables. We need the speed of light. Next, the gravitational constant, mass of the Sun, radius of the Sun. We need to declare the number of layers, the number of layers, the number of basic solids. I set up 1000 layers for each star. Look here, a table G-type. Data starts at the first position. Row number 1 has data. Row number 0 has no data. Data comes from the Internet. Publicly available astronomical data. The first column contains the mass of the star. The mass of the star relative to the Sun. Row 1. The mass of the star is 16 solar masses. The second column of the table, G-type, contains the radius of the star. The radius of the star relative to the Sun. There are 7 rows for 7 types of stars. Data comes from Internet, from Wikipedia, publicly available astronomical data. Based on the data from table G-type, the actual values of the physical parameters are calculated. The parameters of the appropriate spectral types of stars. The values of mass, radius, and volume are stored in the table stars. Look here. Inside the programming loop, the mass value is calculated at the beginning. It's the mass of the Sun times coefficient, multiples of the Sun's mass. This parameter was stored in a table, G-type, column with index 0, P, index of table row, 0, index of table column. Column number 0 contains the parameter of multiple of the mass of the Sun. The radius r was calculated similarly. It's the radius of the Sun times coefficient, multiples of the Sun's radius. This parameter was stored in the table G-type, first column. From this data, the volume can be calculated. V base volume, 4 thirds pi r to the third power. The calculated variables are saved in the table stars. The first column contains the mass of the star. The second column contains the star radius value. The third column contains the volume of the star, physical parameters of the stars. The mass value is converted to kilograms. The radius value is converted to meters. The volume is converted to cubic meters.
Nie w stosunku do Słońca, tylko już w jednostkach takich fizycznych.
The data from the table stars is used for further calculations. Does this look familiar? Maybe it's unrecognizable. See, this part should look familiar. Here are calculated the primitive spheres, the values of the basic physical parameters. We remember radius, surface area, volume, mass of body, gravitational acceleration. Notice, here are the calculated parameters. Here all the calculated parameters are saved. We remember all operations must be performed multiple times. For each type of star, the calculations must be repeated. I have temporarily disabled this construct. I set 1, but it doesn't calculate anything. Variable declaration is here. Nmax, number of rows. Pmax, number of columns. 7 types of stars. 7 columns counting from 1. The program reserves RAM. Now, the program works faster and more stable. The data table does not need to be created from scratch each time. All tables and all data cells are initially filled with zeros. Then, the calculated numerical values will be stored in memory cells. Here, I have already enabled the calculations. Note that the second loop calculates the appropriate parameters. Internal loop. The external loop, P, sets the initial values for the current star type. The appropriate parameter values are loaded from the table stars. The star mass value is loaded from column number 0. The star radius is loaded from column 1. The volume of the star is loaded from the second column. From 1 to pmax, calculations are performed starting from the first row of the table. The average density of the object, rho, is calculated. Next, the radius increment, delta R, is calculated. This is the thickness of a single layer. Notice that the star radius value has been loaded. The variable Nmax has a constant value. The number of layers has been set to 1000. It can be set arbitrarily. Delta R will be calculated. The program already has the parameters set for the selected star type. Now it is possible to calculate parameters for thousands of basic solids from 1 to Nmax. Calculations performed in a loop body. The results of calculations are saved here, the first column for the first type of star. When the program finishes calculating for internal loop, then it will load the parameters for the second star type. The index P will take the value 2. The mass value will be copied from the table stars. Similarly, for the star radius and volume, the average density will be calculated, incrementing the radius delta R. The calculation results will be recorded in the second column. Next, the third column, the fourth, up to the seventh column. All layers and all parameters for all star types will be calculated. This is simple, similar to the previous presented model for one object, one loop. External loop and internal loop in this case. The galactic model must have 2 loops. The calculations must perform for several objects, several types of stars. The data vector is replaced by a matrix. As before, the volume of the layers and the mass of the layers must be calculated. A drawing showing a star. The layer parameters must be calculated. The internal loop should look familiar. Calculations must be performed for all star types. Therefore, there is an outer loop P, from 1 to pmax, for 7 types of stars. Here is verification of calculations. This is a simple summation of values. This option is additional, helps check the correctness of the calculations. The results can be compared with the source data from the table stars.
Tej na początku tam, pamiętacie? I zauważcie, porównajcie sobie
The column with the mass value can be compared with the input data.
Tabelki verif z kolumną z masą dla
Both values are identical. The previous calculations were performed correctly. A similar comparison can be made for the volume. Both values are identical. Everything is done well. Similarly, the gravitational force must be calculated for subsequent layers of the object. We remember that the gravitational force is the gravitational acceleration of the inner sphere times the mass of the layer located on the surface of this sphere.
Jedno mnożone przez drugie daje siłę grawitacyjną danej warstwy. I proszę tu.
Here at the top, the force is calculated. The mass value is loaded from the table M shall, the proper row in the table, and the proper column. Gravitational acceleration for the internal sphere, value 1 smaller. Gravitational force is the gravitational acceleration times mass. Similar calculations must be made for all types of stars. The calculations of force were performed from the inside to the outside. The force values for all layers must be added together, of course. The sum of the layers from the surface of an object to its center. Here, from nmax minus 1 to 1. The internal loop performs the summation operation. The gravitational force of layer n, that is the gravitational force of this layer, plus the gravitational force of layer n plus 1. The force of layer n is the sum of all previous layers. The force that is inside the star has been calculated. Rather, the forces for stars of all types. Now it's possible to calculate the gravitational pressure. The value of the force for layers is known. The area of the layers is known. Definition of pressure. Force acting on the surface area. Here, the pressure is calculated, very similar to that for a single object. The variable S takes on the value of the surface area of the sphere. The variable F takes the value of the force for the selected sphere. The force acting on a surface is pressure. The pressure value will be saved in the variable press. The central element cannot be calculated. The pressure value in this sphere is very similar to the second element, layer number 2. The pressure value is copied to the first element, the central sphere. The error value will be small, that's why I could do it this way. The pressure was calculated, all layers for all objects.
Zobaczcie, tutaj chodzi w tej pętli większej dla wszystkich warstw, jest jeszcze dla wszystkich obiektów jest robione.
Here, at the bottom, the gravitational energy has been calculated. The calculations are very similar to the previous ones. All the necessary parameters are known. The variable V takes the value of the layer volume. The variable P takes the value of the layer pressure. Energy definition, pressure times volume.
P razy V daje nam energię. I ta energia grawitacyjna jest.
The calculated energy is saved in the variable E graph. It is enough to sum the energy values for all layers. In this way, the total gravitational energy of the object can be solved, the gravitational energy for all types of stars. Here, the summation operation is performed. It is a simple summation. The results are shown below.
Obok oraz pod spodem. Także tutaj
mass equivalent to gravitational energy. This is Einstein's equation but rearranged.
energii
Mass
grawitacyjnej z
equivalent to
przekształceniem
gravitational energy.
Einsteina, tak, że E równa się mc kwadrat. Tutaj to c kwadrat zostało przerzucone na drugą stronę i mamy ekwiwalent masy.
Star mass.
Spodem to jest masa gwiazdy.
1% of the star's
Masy
mass.
gwiazdy, analogicznie jak poprzednio, to jest ta masa tej gwiazdy podzielić na 100, czyli to jest 1% tej masy danej gwiazdy.
The percentage factor is the mass equivalent divided by 1% of the star's mass.
Masy gwiazdy. I zauważcie.
The calculation results are shown here.
Wyniki. No. Pierwsza
Gravitational energy of stars.
grawitacyjna, potem mamy to.
Next is the mass equivalent.
Masy.
The mass of the
gwiazd.
stars is copied from the table
Tabelki stars tam na
stars.
początku była obliczona, więc jest po prostu przepisana. Ten
Next
procent,
is 1% of the
masy
star's
gwiazdy
mass.
tutaj jest. No i ten
The
współczynnik
percentage factor
procentowy
at last.
ostatni. Mamy
The parameters of the stars have been calculated.
grawitacyjną
The gravitational energy of the stars.
gwiazdy każdego typu. Teraz
The last column contains important data. The percentage distribution of stars in the galaxy. This parameter allows us to estimate the number of stars of a given type in the galaxy. This is an estimate. The total number of stars in the galaxy is also an estimate.
Mniej więcej, tak szacunkowo, znajduje się w galaktyce. Tak?
Knowing the values of both parameters, it is possible to estimate the amount of dark energy absorbed by entire galaxy. All stars belonging to one type absorb a certain percentage of dark energy. The sum of all types allow us to estimate the total amount of dark energy lost in the galaxy.
A wynik, jaki otrzymamy, to będzie wynik ciemnej energii dla całej galaktyki, dla wszystkich gwiazd. Oczywiście dla obłoków gazowych może nie, ale dla wszystkich gwiazd bez problemu.
The galaxy and the stars within it.
No i proszę.
The table G-type contains selected parameters of the stars. This is the mass and radius. There is one more parameter needed, the percentage distribution of stars in the galaxy, G-proc. The gravitational energy calculated earlier is displayed here.
Już obliczoną mamy, żeby było można zweryfikować. I teraz.
The variable ng gives an estimate of the number of all stars in the Milky Way. Some astronomers estimate that there are only 100 billion stars. This parameter takes different values: 150 billion, 200 billion, 300 billion. Probably the most precise estimate of the number of stars in our galaxy is 400 billion. Therefore, the ng variable is set to 400 billion. You can change this value if you want.
To możemy ją tutaj także zmienić, skorygować na taką, jaka jest właściwa. No niech będzie te 400 miliardów gwiazd w galaktyce.
The percentage distributions of stars is shown here. All important parameters have already been calculated. The last calculations will be saved in the table Galaxy.
Zmiennej galaksy. No tak nazwałem, galaktyka. I zauważcie, że tutaj jest w zasadzie takie sumowanie tego wszystkiego, aby powstał jeden wynik dla ciemnej energii. I tak.
The variable proc copies the value from the table gproc. This is the percentage distribution of stars of a given type in the galaxy. The variable num is the number of stars of a given type in the galaxy. The total number of stars is multiplied by the percentage factor for stars of that type. This is the real number of stars of that type in the galaxy. The variable dark E takes the value of dark energy for stars of a given type.
Liczba tych gwiazd danego typu razy EG, czyli ciemna energia dla konkretnego typu gwiazd. Tak? Jedna gwiazda ma ileś tam tej ciemnej energii. Trzeba to pomnożyć przez liczbę tych gwiazd. Po prostu daje całkowitą energię ciemną dla sumarycznej wartości gwiazd, ale danego typu.
The same is true for the variable dark M. The variable dark M is the equivalent mass value for the stars of a given type.
Dla ekwiwalentu masy.
These are all the calculations. Saving the data.
Już jest tylko zapis tych obliczeń. Zauważcie, że
the calculated values are saved in the table Galaxy. The number of type is saved in column number 0. It is the index of the first loop.
Chodzi on tutaj o z tej pętli. Dalej,
approximate number of stars of a given type is saved in the first column.
Danego typu, konkretna liczba gwiazd danego typu. Kolumna
Value of dark energy is saved in the second column.
Wartość ciemnej energii dla danego typu gwiazd.
Equivalent mass value is saved in the third column.
Ekwiwalentu masy dla danego typu gwiazd.
Notice that the second column contains the gravitational energy, dark energy.
Jest ta energia grawitacyjna, ciemna energia podana, ale dla każdego typu.
For each type of star, there is a specific energy value. Now we need to sum the partial results. Down here is the summation operation, the total result of gravitational energy. Similarly, for mass equivalent, column 3, the result should be summed. This is the result for the entire galaxy. The Milky Way absorbs this value of dark energy at any given moment.
W galaktyce ile tej energii pobierają gwiazdy w każdej chwili.
Smaller stars, larger stars, all stars. The rest of the objects are not included in this model. The calculations for the black hole were performed independently. Object Sagittarius A. You can sum the results of both simulations. It won't change the total results significantly. The total mass of the stars in the galaxy is very large. Stars are the main power of the galaxy. I am sure that this model can be improved in the future. Small improvements to the model can significantly improve the computational results, but that's the limit of what I can do. The maximum I can do right now in the dark energy model. Thank you for watching this episode. Bye!
Cześć!